College Algebra, Chapter 5, Section 2, Exponential Functions. Remember that if r equals m over n is a rational number, then for appropriate integer values of m and n, a to the m over n power equals the nth root of a to the m, where m over n is in lowest terms. In other words, when you have a power that's in the form of a fraction, a reduced fraction, the denominator tells you what root you're taking, and the numerator tells you what power you are raising the function to. So for example, 16 to the 3/4 is the fourth root of 16 to the third, which is 2 to the third, which is 8. Another example, 27 to the negative 1/3 is 1 over 27 to the 1/3. Remember that negative sends it to the bottom, which means the cube root of 27. So 1 over the cube root of 27 is 1/3. We're extending our definition of a to the r to include all real values for the exponent r. In other words, now we're using all real numbers for our power. So here's some additional properties for exponents, and these are going to work for any real number a that's greater than 0 but not equal to 1. A to the x is a unique real number for each real number x. Notice there our variable is our power. A to the b equals a to the c if and only if b equals c. Now that makes sense. If a is greater than 1 and m is less than n, then a to the m is less than a to the n. And if a is a fraction between 0 and 1 and m is less than n, then a to the m is greater than a to the n. Here's an example of each of those last two. The first one, you've got a number greater than 1, which is 4. 4 squared is less than 4 to the third, and that makes sense. The other one is a little less intuitive. So we have 1/2. 1/2 squared is actually greater than 1/2 to the third. And if you think about it, it's just because of the way we work with fractions. 1/2 times 1/2 is 1/4. 1/2 to the third is 1/8. So 1/4 is definitely larger than 1/8. So if a is greater than 0 but not equal to 1, then f of x equals a to the x defines the exponential function with base a. So an exponential function is a function where your x, your variable, is in the exponent. That's why it's called exponential. Your variable is in the exponent, is in the power. The number that you're raising to that power is called your base, and your base will be a constant. Okay, we're going to graph f of x equals 2 to the x and determine the domain and range of f. Why don't you pause the recording and give this a try? Yeah, you can easily graph this on your calculator and look at that and see what you think about the domain and range. Resume when you're ready to check your answer. So here's our graph. It's curving upward, and we have an example of the table there. There's no x-intercept, so it doesn't cross the x-axis. In fact, that's going to be an asymptote. Any number to the 0 power is 1, so it's going to cross the y-intercept at 1. The domain is negative infinity to infinity. There's no restriction on what you can put in there as a power. We can use all real numbers. And the range is 0 to infinity, because if you're raising 2 to a power, there's no way that's going to become a negative number. In fact, you can't raise 2 to a power and get 0. So that's why the range is going to be 0 to infinity, but notice we have the parenthesis around 0. It's not including 0. Now try this. Graph 1/2 to the x and determine the domain and range. Pause the recording, try it, resume to check your answer. All right, do the same thing as you did in example 1. You're going to, you can actually use your graph for this. This is, you can see this done by hand where some points were picked. Notice that it's curving in a different direction. Before it was curving up from left to right. Now we're going down, we're decreasing. And you see the table there. As our power increases, we're getting closer and closer to 0. Now again, we're never going to reach 0. You can't raise 1/2 to a power and get 0. You can get very close, but you will never get 0. So our range is going to be from 0 to infinity, just like before, and our domain is going to be negative infinity to infinity, just like before. A little bit of information about this function. F of x equals a to the x. A is greater than 1. The domain, as we said, negative infinity to infinity, and the range is from 0 to infinity. Now again, notice this is for exponential functions where your base is greater than 1. It's increasing and continuous. The x-axis is a horizontal asymptote, and the graph goes through the points -1, a to the -1, so 1 over a, 0, 1, and 1a. Now this is the summary for the same function, but this time when we have our base is as a fraction between 0 and 1. And notice domain and range stay the same. However, this function is continually decreasing as you go from left to right. The x-axis is still a horizontal asymptote, and it still goes through some of the same points here. It goes through -1, a to the -1, goes through 0, 1, and it goes through 1a. Now we're going to think back to our experience with translations back at the beginning of the semester. Explain how the graph of y equals -2 to the x plus 3 is obtained from the graph of y equals 2 to the x. Remember what the negative sign does and what the plus 3 is going to do. Pause the recording, give it a try, and resume to check your answer. Okay, the negative sign out front is a reflection across the x-axis. The plus 3 is a translation up of 3 units, and you see there the graph. Okay, you're going to use a graph in this example to evaluate 0.5 to the negative square root of 2. What you're going to do is you're going to graph the function y equals 0.5 to the x, and then you're going to approximate the negative square root of 2 and use your table, use value, whatever, to determine the y value when x is negative square root of 2. Pause the recording, give it a try, and resume to check your answer. Okay, so we graphed it, and we determined that negative square root of 2 is about negative 1.414214. And then what we can do, again, is we can use the table if you have it set where you can put numbers in, or you can do second trace and choose value and put in the x value there, and it will mark the point and give you the x and y value. Now we're going to solve 25 to the x equals 125. Now let me give you a hint. The easiest way to do this is to change 25 and 125 into the same number but to different powers. So in other words, there is a number that when you raise it to one power gives you 25, but when you raise it to a different power, it gives you 125. And that's the number you're looking for. Pause the recording, give it a try, and then resume to check your answer. So 25 is 5 squared. So we have 5 squared to the x, and 125 is 5 to the third. When you raise a power to a power, you multiply the powers. So we have 5 to the 2x equals 5 to the third. Now that our bases are equal, we really don't need them anymore, and we can just set the powers equal to each other. 2x equals 3, and solve 3 halves. And then you can double check. 25 to the 3 halves does indeed give you 125. Now we're going to use a graph to solve this inequality. You're going to put it into your calculator and figure out what values of x make this greater than 0. Pause the recording, give it a try, and resume to check your answer. So we're using the graph, and the graph lies above the x-axis for values less than 0.5. So what we do is we find where does it meet the x-axis, and that's when x is 1/2, 0.5, and it's above the x-axis until you get there. Well, that's where it's greater than. So from negative infinity to 0.5, the graph is greater than 0. And this is an application problem. Remember that simple interest is interest equals principal times rate times time, PRT. P is the principal or the initial investment, the amount you're starting with. R is the annual interest rate, and it's given as a percent. T is the number of years. A is the final balance at the end of each year. Then, the first year, you would have P plus PR, just P times 1 plus R. At the end of the second year, you would have P times 1 plus R, which is what you had at the end of the first, plus, now your additional interest, P times 1 plus R times R. And then when you sort all that out, that's P times 1 plus R squared. Now you could continue this pattern. You end up with an equation that looks like A equals P times 1 plus R to the n. And what we were doing there is we were working on the derivation of the compound interest formula. Compound interest is when the interest is calculated periodically and then added into the account so that the interest begins to earn interest. And it's a way of making your money grow faster. Suppose that the principal of P dollars is invested at an annual interest rate R in decimal form. Remember, you need to change percent to a decimal, compounded n times per year. Then the amount A accumulated after T years is given by the formula A equals P times 1 plus R over N to the NT. So principal times 1 plus the rate over the number of times compounded to the power of the number of times compounded times the number of years. So try this example. Let's say you invest $1,000 at an annual rate of 4%, compounded quarterly. There's the key. Quarterly means 4 times a year. Find the total amount in the account after 10 years if no withdrawals are made. Pause the recording, give it a try, and resume to check your answer. So putting all the numbers in place, we get $1,488.86. Notice that our money is rounded to the hundreds place. It doesn't make any sense to go beyond the cents. Now we have this number symbolized by a letter, another one here. It's called the natural number, and the letter it's symbolized by is E. It's named after the Swiss mathematician Leonhard Euler. It involves the expression 1 plus 1 over k to the kth power. And the idea is that as you take this 1 plus 1 over k to the kth power and you push it to infinity, as you make it go towards infinity, you end up with, it converges to a number, 2.718281828. And it actually is not a repeating number. If you go beyond there, the pattern stops. That letter is called, that number, sorry, is called E. It's used, the letter E is used to designate it. And it is an irrational number like pi. It doesn't end and it does not repeat a pattern. It's an important base, and calculators are programmed to find powers of E. In fact, your calculator has it in 2 spots. One of them is on the ln key. You'll notice if you hit second and then the ln key, you get e to the x. It sets you up ready to put a power to it. And there is another one on the calculator also. I tend to use the one on the natural log, the ln key, for various reasons, but one of which is it gets you ready to put a power in right afterwards. This is a graph of e to the x. Notice it looks similar to the graph of a to the x of any number to the x, has its similarities. Now, we use E in an interesting formula called continuous compounding. If an amount of P dollars is deposited at a rate of interest R and is compounded continuously for T years, then the final amount in dollars is A equals P times E to the RT. The idea behind this is that instead of compounding it quarterly or daily or even hourly, it's compounding every second of every day. Now, believe it or not, that does not mean that your money is going to grow wildly and uncontrolled. It actually reaches a point where it levels off. And the amount of change is so tiny, it doesn't make a difference in the money amount. So this formula determines the amount of interest that you receive, or the amount of money you have, after a certain amount of time when you have money in an account that is being continuously compounded. So try this example. Suppose you have $5,000 and you put it into an account paying 3% interest compounded continuously for 5 years. Find the total amount on deposit at the end of 5 years. Pause the recording, give it a try, and resume to check your answer. And there we go. Just put the numbers in and put it in your calculator and you get $5,809.17. This problem is another application. We're going to model risk. The chances of dying from heart disease increase exponentially after age 40 according to the function f of x equals r times 1.11 to the x, where r is the risk in decimal form at age 40 and x is the number of years after 40. Compare the risk at age 75 with the risk at age 40. Now I know we don't know what r is, so just leave that as r. Pause the recording, give this a try, and resume to see how you did. Okay, so x is going to be 35. That is 75 minus 40. So we have r times 1.11 to the 35th power, which is 38.6 r. That means the risk is almost 39 times as great at age 75 as it is at age 40. Problems for you to try. Pause the recording, try them, resume to check your answer. Do this until the end of the recording.